Welcome everyone and thank you for joining us for the final session of our Expert Sessions webinar series. These short webinars have taken place every 2 weeks, each lasting no more than 30 minutes and have brought valuable insights from the industry experts. Today's session will be presented by Sonny Solanki, who's Senior Technical Manager at I-Gard. Sonny is an electrical engineering by McMaster University with 8 years of experience in protection systems and relays. Through his career, he has educated consultants and end users to the benefits of integrating electrical protection products into their designs to enhance personal and equipment safety. He specializes in providing commercial and technical support for various projects and applications, including high-resistance grounded systems, low-resistance grounded systems, hybrid HRG systems, ground fault and arc flash protection systems, resistor-based solutions, and personal protection products. We are excited to have him with us for this closing session, and we truly appreciate your participation through the series. Thank you for your time, and thank you, Sammy.
Thanks, Andrea, for the introduction. Today's presentation is on IEEE 43 requirements for insulation resistance testing and the significance of polarization index and dielectric absorption. There are many ways a motor can get deteriorated over a period of time. Motors typically degrade due to wear and tear. There can also be stress factors such as frequent starts and temperature fluctuations can cause insulation to crack. In addition to that, when you have a very high moisture area, idle periods allow moisture to build up, reducing insulation resistance. And also, if unchecked, degradation leads to unexpected motor failures and costly downtime. IEEE identifies approximately 30% motor failures as insulation related, and that's coming from IEEE 2002. So you need insulation monitors if your production conditions involve high humidity, dust, wetness, a corrosive environment where there could be even fumes in the air as well. So the IMX relay that we have, and we've updated based on market input, activates only after system voltage and capacitance have fully dissipated. It conducts a 10-minute insulation test calculating the polarization index, denoted as PI, and a dielectric absorption ratio, designated as DAR. It automatically shuts off after testing, so no continuous 5,000 volts DC voltage is applied. It's only during the test period that we apply that DC voltage. And before re-energizing the machine, operators can press the test button to perform a second 10-minute check before the machine comes online. This behavior aligns with preferences from industry and ensures both safety and compliance with IEEE 43 and NETA MTS-2019. So the two approaches in the market today are to have a fixed relay with set points measuring cable insulation when the equipment is de-energized. So this is insulation monitoring, and it's usually a permanent installation. The applications that we involve ourselves in are in between 600 volts to 13.8 kV. The test activates once the system voltage decays and performs time testing on the PI and DAR, and automatically shuts off, preventing that continuous 5,000 volt DC exposure. We test the insulation at NETA rated levels ranging from 250 volts DC to 5,000 volts DC, depending on what your line-to-line voltage is. We provide an alarm if the insulation level drops below a preset level, and we also have a self-test feature within the relay to confirm that it's still working as it should. The other method is to measure the system, and this is typically done with a portable test equipment. Insulation resistance testing is conducted periodically using a DC resistance test set and calculate the dielectric absorption and or polarization index values for trending analysis. A change in the ratios could indicate a potential problem to be addressed. So why should we focus on the trending? Well, individual readings may vary due to environmental factors such as moisture and temperature, and trending often reveals patterns indicating insulation degradation over time. So IEEE 43 recommends to perform for machines that are greater than 200 horsepower to perform a 10-minute test to calculate the polarization index. For systems that are below 200 horsepower or equal to 200 horsepower to conduct a 1-minute test calculating the dielectric absorption ratio or DAR. The key standards that are important with respect to these tests are IEEE 43, which is the recommended practice for testing insulation resistance, and NETA MTS-2019, which requires testing under IEEE 43 guidelines for critical equipment. Now in this graph, we're going to explain what each of these current readings are. So we have current on the y-axis, and then we have the seconds from 0.1 to 10 seconds. So to start off with, the capacitive charging current, we want that to drop off completely to a low value before we initiate our test. So the current starts off very high as the capacitance is discharging, and then it goes down to a very low value of current. The absorption current is also initially high, and then it drops off after 10 seconds. And the conductance or leakage current, which is in relation to this line right here, is a small, essentially steady current both through and over the insulation. So with good insulation, the conduction or leakage current should build up to a steady value after just under a second, and then it reaches a steady state where we can get an insulation resistance reading. And over here, what we're measuring is the total current of the absorption, the capacitance, and the conduction or leakage current. The total current is basically e to the negative t over RC, because we're dealing with a resistor capacitive circuit when we're applying our DC voltage, and we're capturing that current to determine the insulation resistance value. Now in IEEE 43, NETA MTS-2019, and NFPA 7dB, they mandate insulation resistance tests for calculating dielectric absorption ratio and polarization index. For the dielectric absorption ratio, ratio of 60 seconds resistance to the 30 seconds resistance is compared and indicates short-term absorption of insulation. For the polarization index, it's actually a ratio of the 10-minute resistance to the 1-minute resistance, and it highlights the long-term dielectric behavior and moisture effect. So you could see on the table on the right here that we have insulation conditions as our first column, our DAR in our second column, and our polarization index in our third column. What's considered dangerous is a value below 1 when it comes to the DAR ratio. For the polarization index, it's also the same, anything less than 1. What's questionable is if your DAR ratio is between 1.0 to 1.25 or between 1 and 2 on your polarization index. A good value for the DAR value would be 1.4 to 1.6, and on the polarization index it would be between 2 to 4, and anything above 1.6 would be considered excellent insulation condition for the DAR, and anything above 4 on the polarization index would be excellent insulation condition. Now, with respect to NETA MTS 2019, it recommends using a minimum DC test voltage based on the equipment's nominal voltage. So IM relays can produce a 5,000 volt DC test voltage, enabling insulation monitoring and testing on systems up to 34 kV. So on the table on the right, we have nominal rating of equipment in volts for line-to-line voltage, the minimum test voltage in DC, and the recommended minimum insulation resistance that would be corresponding to that line-to-line voltage for your system. Why should we test at the full rated voltage? This ensures insulation can withstand the maximum operating voltage and detect weaknesses that could cause failure under actual conditions. The outcome is that we confirm insulation strength and identify weak points and provide a safety margin for high voltage application. So the new IM relays are designed to prevent continuous exposure to the full 5,000 volt DC test voltage. Testing begins only after voltage decay, and it runs for 10 minutes to calculate PI/DAR, and then the voltage is removed. This behavior aligns with user preferences and preserves insulation integrity. So at I-Gard, we are using our IRT relay, which is coming soon, and it combines insulation monitoring and resistance testing in one device. So it's continuously monitoring of de-energized equipment, periodic testing with the dielectric absorption and polarization index. We have data storage and Bluetooth connectivity for trending analysis, full compliance with IEEE 43 and NETA MTS 2019 standards, as well as delay tests start until system capacitance has dissipated. So you saw on the graph previously, we were waiting for that capacitance to drop off in terms of its current, and a 10-minute automated testing with PI and DAR calculations. There's an auto shutoff after testing to avoid continuous high voltage application, and a manual retest function before re-energizing the equipment so that you can confirm that the motor would be available to come online after that test is completed and the values are within range of a good insulation resistance reading. So stay tuned for the IRT relay launch, your complete insulation testing solution. This model will go between 600 volts to 13.8 kV, and it would give you indication as seen here on whether your insulation is good, there's a caution, if it's regular, or if it's in danger. If you have any questions, feel free to ask them and we'll cover them right now in the questions pane. Is this testing considered destructive? I wouldn't say so, because we're keeping in line with respect to our test voltage in accordance to your line-to-line voltage of your system. So typically, let's say for a 600 volt system is testing for 1000 volts DC. That would be the test that we put on it. And typically the insulation values on a 600 volt system would be able to handle that for a short period of time. Is it offline testing for these relays? Yes, it is offline testing. So after the motor's de-energized and the capacitance has discharged, then we begin our testing by applying that DC voltage to your system. And the DC voltage that we're applying varies depending on your line-to-line voltage. So is the industry using this instead of doing offline testing? Well, as I mentioned, there's two different methods. Some people are using a megger to test for insulation resistance and then determining the polarization index or the dielectric absorption ratio, while others are using a permanently mounted solution like ours to monitor this. Does the alarm on the instrument stay on even after the system is energized again? I believe it does stay in alarm, and depending on how your dry contacts are figured, it may not allow the motor to come online if it's connected to your trip circuit. But I can inquire further as to whether it's latching or not. What about insulation testing recommendation for large 480 volt motors, e.g. for greater than 200 horsepower? So for greater than 200 horsepower, we would use the polarization index test, and then we would do a 10-minute test where we would take the ratio of 10 minutes over the 1 minute reading and provide that polarization index value. If the value is between 2 to 4, then that's considered good, or even 4 or greater is considered excellent. Have you seen any situations where the insulation is good but DAR is not for the motor? Well, the DAR is calculating the insulation resistance, so I don't think we've seen anything which is indicating like a false positive or false negative in the field, but maybe I can get more information from my manager to see if that has occurred before. You spoke earlier about testing systems at or above full nominal voltage, but the chart indicates testing of 34 kV lines with 5000 volts DC. Does that still work as well? I mentioned that we're going to apply a test voltage in DC based on the line-to-line voltage that you have as per that table 100.1. So for a 600 volt system, we would be applying 1000 volts DC. For systems that are 13.8 kV or higher, we're typically applying 5000 volts DC. So this is like the method to test for insulation resistance, and that still works for systems that are at 34 kV. Does this apply to oil type transformers? I'm not sure if it applies to transformers, but mostly we are dealing with motors and generators for this application. What is the recommendation for the use of this relay? Should it be a preferred installation on critical larger motor applications? It's entirely customer dependent, depending on the criticality of the motor as well as the size of the motor. If it's a very expensive asset, I would imagine that they would want a permanently mounted and permanent installation method to collect the trending data to see how they can mitigate major damage and try and repair minor damages when they see that the trending analysis is going in such a way that indicates that the motor is going to be prone to failure on the next energizations. Do you recommend permanent installation of insulation and resistance monitoring relays at 25 kV cables? This is more in relation to motors and generators, so I can't comment on whether it can be used on cables or transformers. Can a motor be restarted while the testing is ongoing? I don't think so, because the test will detect the voltage and shut off. You imagine this product would work for grounding systems? I'd have to get back to you on that as well. We're mostly focusing on motors and generators with this product. Is PI used in HV? And if you have any further questions, you can email us at support@i-gard.com. It's written below right here, and we look forward to those questions. This is our last expert session, so we're collecting all of the frequently asked questions throughout each of the expert sessions, and we're going to be providing answers to them in a document, and we'll be sharing those with you. We just need a bit of time to go through all that data, since it's a lot to go through, and then we'll provide our responses accordingly. I hope you enjoyed the presentation, and feel free to reach out to us for any of your applications where you need assistance. We hope you appreciate these presentations, and we look forward to seeing you again on the next set that we plan on doing in the future. Thank you.